My name is Teja, and I got a PhD in CS, but I had a lot of interactions with operations research and operations folks, and in fact, I ended up in a business school eventually. Some work in industrial, I guess in the industry, some patents, and some research papers on the academic side, and I have a few experiences here and there, Apple, Citadel, in finance and other areas. So really happy to be here, and if you want to chat about any of these other topics, I'm here. Let me get to the goal of this short lecture. As we saw, there were some parts, analytics was playing either a supporting role or a core role in some of the topics that you saw in this course. And as Raga said, this is a field where a lot of things are changing, especially analytics. I mean, if you've played with large language models or generative AI tools, you know that there's a lot of enthusiasm in that area. And we, as in the operations and supply chain field, we also get to gain some benefits from that field. Okay. And so my objective is to really show that there is a nice complementarity, and show some example snippets of some of the things that I have worked on in terms of using some analytics tools in some operations problems, and also show that there are gaps. Okay, and that's where you come in. We are domain experts in operations, and there's some cool tools being built in our sibling industry, and we want to kind of use them to do well in our businesses. Okay. So I'm going to do that with a few applications. So it's really going to, and the format is going to be mostly, I'm going to introduce the problem, the context, some element of analytics and operations, and some learnings from that. Okay. And so there are going to be 4 applications that I'll try to cover. The first one is related to crowd shipping in transportation. So I'll discuss what crowd shipping is in a second. It uses a particular tool in the field of analytics or in the field of machine learning called reinforcement learning. Okay. So it's about reinforcement learning is about some decision making, how to make good decisions, but that's some analytics tool that will be used to do well in this crowd shipping problem. The second application is called choice modeling. Choice modeling is actually a very traditional area in operations. It's an area called revenue management. I don't know if it's taught here as a separate course or not, but there's a whole field of revenue management of how to price and how to show assortments or offer sets to customers. And so how does machine learning or analytics tools bring some extra ability in this area, okay, in the area of choice modeling, either in terms of optimization or in terms of just modeling choices of people. Okay. The next 2 applications are actually I put them in here, although they are a little bit different from the operations and supply chain focus we have in this course, as a way to show you that there's still a gap between the analytics tool and the application. Okay, and that's where either the tool builder, like a machine learning person or whatever, can try to adapt the tool and say, hey, here's a tool that you can plug and play in your application, in your operations application. Or we as domain experts have to recognize that, hey, there's a tool out there, here's my operations problem, there's a gap. Okay, and I as a domain expert will probably be better at identifying that gap, and if you can actually bridge that gap from your end, you can actually be a great enabler in business success. Okay, so these 2 applications, one of them is related to computer vision in manufacturing setting or transportation setting. You can, I'm going to discuss that, but it's mostly about computer vision tools that people build, vision tools. They are not enough for this particular manufacturing or transportation setting, and so how do we bridge that gap? And they're simple ideas. Okay, you're not training new models, you're not training any new regression models, anything like that, but you want to kind of still bridge that gap. Use that tool that's built for your purpose. And the last one is an application of using LLMs. I think some of you might have used ChatGPT or Bard or any of these other ones. The question is, how can I use that for my business application? And I'm going to show it in a particular form. Obviously, you can use LLMs to generate new text, creative writing and all that. But can we do that? Can we do something which is actually useful to my business in terms of operations or strategy? Okay, and this is going to be a little bit closer to the strategy side of things. Okay, so let me actually get started with the first application. This one, as I said, is in transportation. Okay, so crowd shipping. So what is crowd shipping? Crowd shipping is about shipping products from point A to point B using a crowd of ordinary individuals. Okay, so these are basically on demand. It's a gig working setup. So you have people who will call crowdsourcees, and these people will help you ship or basically get a product or whatever, parcel from point A to point B that's requested. Okay, so think of it that way. So that crowd shipping is a has many incarnations in terms of like different companies are kind of using gig workers in different ways. But there is actually a need for that, irrespective of how the business models play out. That's because there's been a rapid growth in e-commerce in general, at least in the United States. So I'm just talking about the United States, but you can include Canada, you can include many different locations. Just one stat, I think. So just the food delivery revenue. Okay, I'm not even talking about anything else in the food industry. I mean, obviously there's preparation. There's ticket prices that you get from selling food, but just the delivery component is worth $30+ billion, right? Just the delivery part. So you can imagine how much operational efficiency that you can put in, and therefore get those margins bigger than they are. The interesting part of crowd shipping is that there's a huge time-sensitive nature of this delivery. So you want to deliver, for example, food within an hour or two, right? Two actually is bad, probably within an hour, right? Secondly, actually, there's also some sustainability aspect to this, in the sense that should you have like dedicated trucks or dedicated vehicles moving around urban neighborhoods, or do you want to actually utilize people who may have bandwidth and who may actually want to have that extra income? Can you use them, right? So that's the context for this problem. And where does so this is a problem, and that's the context. And what is the operational problem, right? The operational problem is we want to match things. Okay, crowdsources arrive dynamically on the platform. Let's say we have a platform like in our company, and requests also arrive dynamically. And when requests arrive, they say, okay, pick up point A, drop off point B, and time limit is 2 hours or 1 hour. Okay, so given this information, this data, the operational problem is to just match them, right? Match crowdsources to requests, and not just one request, not 1:1 matching, but a crowdsourcing hopefully can do 5 requests, and they have a particular route that they can take, right? So it's an assignment problem, some variation of an assignment problem. And while you're doing this matching, what you want to minimize is some sort of shipping cost, right? So how does shipping cost come into play? So maybe when the crowdsource is idle, you don't pay them. But when you're asking them to go to point A and therefore pick up something and go to point B and drop it off, they are being, they're charging you. Okay, there's a cost per unit time that you're using that resource, these crowdsources. And it also depends on how complicated your routes are. So maybe the crowdsource is going, zigzagging throughout your urban area, then it's going to cost you a lot. Okay, if you have assigned it in a very bad way, assigned the crowdsources to request in a bad way, right? And also you may have some, you have time limits that you need to honor, and your customers will not be happy if something that was supposed to deliver within an hour is going to be delivered 30 minutes later or an hour later, right? So you may need to have some backup plan, and so there's a cost of that backup plan, right? Maybe a backup vehicle, right? So this is what you want to minimize, and so this is a pure optimization problem, the way I've stated it, right? There's some constraints. People can only carry some amount of food or some amount of whatever goods, and there's request constraints as well. Like you can't deliver later than what people have asked, right? So that's the operational problem. Where does machine learning come in, or machine learning or analytics come in? Is that this problem, this matching problem, you can solve it using, at least historically, people used to solve it. Even today, it's basically solved using what I call heuristics. Okay, I don't know if you have been exposed to the idea of heuristics. Basically, these are approaches or ideas or algorithms. Algorithms just means a sequence of steps in a procedure. There are ideas where there's no guarantee. Okay, there's no guarantee that it actually works. The word optimal doesn't make sense. Okay, here. So these are this is the set of tools. These heuristics are the way to solve these problems, these real-world hard problems, computationally hard problems. And there's a whole field. Okay, it's been it's like a multi-decade research area, and that's what actually people use. Like if you go to Walmart.com and say they'll deliver in the next 5 hours, they're actually using heuristics, because you can't really solve this optimization problem using any of this linear programming, integer programming, and all that fancy names that we study in courses, right? So we can solve this matching problem, in our case, the crowdsourcing request matching problem, using heuristics, or we can use another heuristic using an analytics tool, okay, using machine learning. In particular, the tool that I want to mention about is called reinforcement learning. Okay, so reinforcement learning, I don't want to, for our context, it's going to be a black box. What does it do? What does it do? There are certain types of problems called sequential decision-making problems, where the action you take today has a long-term consequence. I think there's some form of this you might have seen in inventory settings and so on. Okay, where if you stock inventory low now, there may be a downstream effect of something else that there may be a cost to it later on that you will realize. Okay, so in our case, when we match people, when we match a crowdsourcing to a request, what is the request? You can match it. Let's say there are two types of requests. Let's say the crowdsourcing is in some location northeast of Toronto, and there's a request that's in southwest of Toronto, and there's a request also in northeast of Toronto. So the question is, should I just match the guy to the request that's in the same neighborhood, or should I match the guy in the diametrically opposite place? Okay, there is no right answer, in the sense that the decision you make could have a longer-term consequence. Maybe you would want to match this guy to the diametrically opposite place, because at that place, maybe you anticipate there's going to be future demand. There's going to be a new request that will come up next hour. Okay, so this is like you take a hit now, you're making the guy go all the way across, but you actually are in a better position to serve a request later on. Okay, so there's a long-term consequence of actions. Okay, that's something that reinforcement learning helps solve. But let's come back to the crowdsourcing problem. So we want to solve this assignment problem of assigning crowdsourcing requests using reinforcement learning. And there are some ideas already in the analytics field or machine learning field which solve the reinforcement learning problem in general. So any situation, how do you map that into a reinforcement learning problem? Once you map it, there's a huge set of algorithms that you can just use, and you will do well. Okay. What we do in this paper with a few colleagues of mine, we actually specialize that reinforcement learning toolbox, or whatever, not toolbox, but the tool, the black box, to our setting where we know that heuristics work well. Okay, we know historically people use heuristics, and so we kind of merge this analytic tool with what we know works well in this domain. Okay, and let me mention that, like, how do you merge heuristics? Heuristics are, as I didn't mention how exactly heuristics work. They are basically, you start with, hey, let's match something, as in match some crowdsourcing to some request, and then let's see if we can locally improve it. Let's look at our solution and then say, oh, maybe this crowdsourcing, instead of matching with this request, maybe change it to this something else. Okay, that's like a very incremental way of doing it, and that's exactly how heuristics work. It's up to first approximation. So how do we mix heuristics with our machine learning tool? Is that we'll make the machine learning tool take a higher level decision. Okay, remember the decisions have to be non-myopic. There could be long-term consequences of my decision, but the machine learning tool is going to only make decisions at the level of, okay, at the level of what is called choosing a heuristic type, rather than actually performing the heuristic. So the heuristic types are what's listed here: insertion, two intra-root moves, and so on. Okay, let me not get into the details of these heuristic types that the ML tool, the reinforcement learning tool, picks, but I want to show you what insertion means. Okay, so let's say this biker over here is our crowdsourcing, and they have been currently assigned, okay, pick up something from there and go to this destination. Okay, insertion just means when the machine learning part, the algorithm shows us, okay, let's try an insertion type heuristic. All it's saying is, okay, for this crowdsourcing, should I be inserting an extra request into their route? Okay, that's what insertion means. Among everything else that I could do at the current situation, in the sense that, remember, I'm not solving just one crowdsourcing and a bunch of requests. I'm actually having 1,000 crowdsourcings and maybe 1,000 or 2,000 requests. Okay, it's a big problem. It's unclear what to do, how to slowly build up a solution, a matching between this crowdsources and requests. And to slowly build that up, at each kind of micro step, I need to figure out whether I should do an insertion. If I do an insertion, which crowdsources should I add this extra request to, for example, right? So which crowdsources I add this request to is a heuristics level problem. To actually take that insertion as the action to the micro step that I need to take is the decision made by the machine learning part. Okay, so you're splitting these two, combining these two, and trying to get better solutions. I'll not get into the detail of the ML portion, but I want to say that there is some neural network involved, and this is what we borrow from the ML folks, the machine learning folks, and let me directly get to some results. Okay, so I just want to show you that this idea of not just using pure heuristics, which is the previous state of the art, but using some amount of machine learning actually gives you better in terms of the shipping costs I was talking about. So the purple bars are, and this, by the way, is just a collection of instances where I'm trying to show, because different instances have different shipping costs, right? Different situations, different crowdsources, potentially different requests. So I'm just trying to show you that we can actually do much better than these heuristics. And don't even talk about this integer programming and stuff, because that's not even going to be in the same realm of, they may do well in terms of costs, but they'll take months to solve, and we don't have that time, right? We have to solve this in a minute, in a few minutes, so that we can actually assign our crowdsources to requests. Okay. And this, in the second graph, I'm just showing that, okay, even if you have variations, like maybe there's different demand patterns during peak hours, maybe during dinner time, for example. So you can still, we show that we actually do well in terms of total shipping costs. Okay. So my objective with this application is not really to get into the details of the reinforcement learning approach or how it exactly is applied, but I wanted to show you that we can actually improve operations by really relying on some of the advancements that are being made in machine learning. Okay. Let me actually switch topics. Any questions here, by the way? Yeah.
Would that be possible to go on the first slide, please?
Yeah.
First one.
Yeah.
Yeah. So the second point under rapid degrowth, the food delivery ones.
Yeah.
So I see the delta is really high, but
yeah.
In one of our previous courses, we did some analysis on DoorDash.
Yeah.
And we found out that most of the food delivery companies are running at loss, not even at break even.
The delivery companies, yeah.
Food delivery companies.
Yeah.
So I didn't understand that how the revenue is projected like by 32.
This is the TAM, right? It's not specific to any company. Okay. The total addressable market is $32 billion. Now, whether DoorDash is making loss or profit depends on their business model. Like they could be chasing growth, right? I mean, I think, yeah.
When we were discussing that, we found out like almost every food delivery company is running at a loss. So
yes, running at a loss because they want to grow, right? So it's a market, and you can decide whether you want to take the profit now or whether you want to run at a loss and actually reap huge benefits later, right? That's not. I think that's not exactly answer. That's not a counter argument to this number. You need to think. It's not a one-dimensional thing where if all the food delivery companies are making a loss, how can the market size with this? Right? I don't think food delivery companies maybe can still be making loss, all of them, and still you can have a market size of that. Yeah.
So that's like saying if you give freebies, a lot of people will sign up.
Yes, that's what they're doing right now. Yeah.
Because nobody's made money, how do you know it's a business model? Maybe it's just charity.
That's a good question. That's a good point. It's a charity. I mean, generally, for many VC-backed companies, I mean, as you know, right, the success rate is like 1%. Let's say, even being generous, 1%. The 99% of the bets that they make is actually a charity. Yeah, it is a charity. The 99% which did not work out, but the 1% that work out are like huge wins for that that deal flows, right? Yeah. So your point is correct, but this is just a total addressable market that I'm commenting here. And this, I think, statistic is from a company called Statista. I think it's a pretty popular source for these types of stats. Okay, let me actually get to the second application, second use of analytics. This is choice modeling, and this should be like something that if you have not seen, it's actually the bread and butter of revenue management, or a part of the bread and butter of revenue management. What we're going to do is, again, intersect that with machine learning. And when I use the word analytics and machine learning, I'm just using it interchangeably here. So what's the objective, right? So businesses want to optimize things, optimize what they want to show to customers. Okay, and and generally you would see in choice modeling, the first, if you see any graphic, it's going to be about retail store optimization. Like, okay, should we put bananas next to apples, or like soft drink 1 versus soft drink 2, things like that. Okay, here I'm showing a little bit non-standard situation. This is just a tweet. Tweet has a lot of features, but think of it this way, right? So when you open your phone and you go to x.com or whatever, twitter.com, and you see a few tweets, out of the millions of tweets that happened in the past 30 minutes or maybe that day, why should those 5 tweets be shown to you? Okay, why those 5, right? So there's a reason why they're showing those 5 and not the other 495,999 something, right? The reason is they want to maximize engagement, right? The businesses want to maximize, in this case, engagement, but in retail case, they want to maximize profit. Okay, and so, but what is the premise of even this engagement maximization thing is that what if the tweet topic, what if all these tweets are about, not in this case, but what if all the tweets are about the same exact maybe news, for example, right? So then wouldn't me interacting with any one of those tweets be dependent on the other tweets, right? If it's the same news topic shown 5 times, then I'm less incentivized to respond to any one of them. Like, so what I'm trying to say is that even in this problem, there is a neighborhood effect. Okay, what you do with one tweet, like if you engage with the tweet, maybe retweet, comment, or something, depends on what else was shown over there, right? So this is exactly the problem in retail as well. In retail, me picking, let's say, a particular soft drink depends on what other healthy or non-healthy options are next to it. Okay, that influences. There's a neighborhood effect, and that's exactly what choice modeling is about. How does user choice get influenced by what you get to show the user or the customer, right? So I don't know if you've seen this type of representation of the problem. Before I get to the title, which is about machine learning, the choice modeling problem is formulated this way. Okay, you have a bunch of prices for your n products, little n products. Okay, let's say they are ordered, but it doesn't matter. The little n number of products. Okay, soft drink 1, soft drink 2, soft drink 10. Okay, 10 products. Now you have to choose, let's say, 3 soft drinks to show among these 10 soft drinks. Okay, that letter capital S represents that assortment or the set of 3 soft drinks that you get to stock in your little store, given these 10 different types of soft drinks that you could have used from. Okay, so what 3 to show? Like you can say, okay, all these sets of soft drinks that I can show is too many, right? So 10 means 2 to the power 10 number of subsets of soft drinks that I can show. Okay, this is just a basic calculation. But if you had to show exactly 3 out of 10, maybe there's like 10 choose 3 or some sort of calculation. You can say, okay, these are all sorts of 3 sets from the 10 potential soft drinks that I can pick and show, right? But how do companies do it, right? So how do you kind of optimize for what to show? Is first you kind of build what is called a choice model. What is the probability of a customer purchasing product I, soft drink I, given what I show? So this very fancy notation is just saying that what's the probability that the customer is going to pick the ith product or the ith soft drink given I show soft drink 1, 2, and 3. So what's the probability of picking 1 given soft drink 1, 2, and 3? What's the probability of picking soft drink 2 given soft drink 1, 2, and 3, and so on? Okay, so there are only 3 numbers here because there are three things to show. So that's the choice model. Okay, this is exactly what is called a choice model. What's the probability of customer doing something given what I show? Okay, that's what a choice model is. And given such a choice model, generally the store operator or the person who wants to kind of optimize the set has that type of an optimization problem. It's just saying, okay, if the person chooses item I or soft drink I, there's some revenue I can get, some price with which I can sell it. But the customer can choose I or J or whatever, like all the 3. So let me just average out. Let me get the expected revenue of the expected revenue I can get from the customer or from my demand if I show this if I pick these 3 soft drinks, okay, for my store. So it's an optimization problem. All I'm saying is, if you can somehow build this choice model, this capital P thing, then you have an optimization problem that you have to solve to figure out what is the best things to show or best things to keep in your store. Okay. The question is now, can we use machine learning to actually even solve this optimization problem? So think of it this way. I'm not even asking us to build a choice model. I'm saying, can we solve the optimization problem? Okay, it's a different application of the same analytics tool, the same machine learning black box. Like, think of linear. When I say machine learning, just think of linear regression, because many of the other things are just non-linear versions of them. But here I'm asking, can machine learning help with optimization? Okay, so in terms of, so let's get a sense of the optimization problem for a second. Let's think of the retail setting, which is, I guess, a little bit more common in like revenue management. For example, Walmart has 20,000 SKUs, or think of them as products, 20,000 SKUs for just cookies, right? And let's say it carries 500 such SKUs at a store. Okay, how do you get from 20,000 to 500, and why those 500 for that demographic that that Walmart store serves, right? That's the problem. That's the assortment optimization problem that Walmart has to solve. But that's can be a slow problem. They can solve it over a few weeks and then figure out, okay, let's order all these 500 different cookies and then let's store the cookie section, right? But the same problem also happens for e-commerce platforms as well, right? The Twitter example was just an engagement example, but you have a screen size, right? You have a limited screen size. You want to show 5 tweets, or you want to show 10 products, like let's say you go to Amazon or whatever. Why those 10 products out of the million products that they have, right? So it's the same type of problem, except the time scale now is within seconds, right? You don't have a week to solve this problem. So can we actually solve this optimization problem using machine learning? Okay, it's 2 levels non-trivial, because I'm not saying let's build a choice model using machine learning. I'm saying let's solve the optimization problem using machine learning. So actually we can do that, and this is where I think if you know the domain, you can actually see, okay, what ML tools are out there and actually map them to your problem. And that's where we've been, in fact, the previous problem was also like that. That's what we're going to do. Okay, so let's pick a choice model, and that choice model happens to be MNL. Okay, so multinomial logit is the name of the choice model. It's a pretty old choice model, 30+ years, I think. So it's a model which has little n number of parameters, 1 per product. Okay, there's one number per product. Okay, some number that you can compute, you can estimate using data. Okay, just like doing linear regression, you have a bunch of coefficients. Here you have one number that you can compute per product given your data. Okay, once you do that, the model says that, okay, once you compute that number, this is how your probability is going to be. The probability of choosing item I is just going to depend on that number divided by the other numbers, divided by all the numbers. Sorry. Okay, so it's a nice formula that you can get just because for this model. Turns out, if you choose this model for your optimization problem, as in you get to choose which choice model you want to use. Let's say you want to choose this choice model to use. Then, because of this nice expression, that optimization problem can be mapped to a nice problem in machine learning called the nearest neighbor search problem. I don't know if you've done ML 101 type of a course, but nearest neighbors is like the first tool that they kind of expose you to, and it's actually a very versatile tool. It actually is one of the most underrated but really good tools in machine learning. So what in this application, what we did is to actually map that assortment optimization problem that I showed you in the previous slide to this nearest neighbor search. Okay, nearest neighbor search just means here's a bunch of data points, like some bunch of points. Here's a query or some new data point. Tell me what is the nearest neighbor to this new point. Okay, and you can actually find that very efficiently, because a lot of ML effort has been gone into how to scale that nearest neighbor problem to billions of points. Okay, so if you can do, and that's really the trick of the second application, is to map the optimization problem to a problem that we know how to solve in machine learning, and it's constantly being improved. Okay, so companies like Spotify have to do nearest neighbor search for finding out songs similar to a given song. Companies like Uber have to do nearest neighbor search to find, okay, what's the nearest points to this some location or some request, and so on. Okay, so there's a lot of variations of this problem. So in this slide, I'm just trying to show that if you Okay, let's actually look at this. So if you, so this nearest neighbor search based approach, this green line, actually beats even linear programming. Linear programming is like linear regression analytics, and linear programming and optimization are kind of similar. They are a kind of solved problem. If you can formulate your problem as a LP, you're in really good shape, because there are really scalable algorithms for solving that. Okay, actually, and we show that if you can map your problem back to this nearest neighbor search, you can actually do better than LP in a certain regime. So that's actually a big gain. Okay, and here obviously the number of products and number of items is the same as number of products, is 15,000. You can say the amount of time is needed is actually very, very close to the time that is needed for e-commerce platforms to actually operate. So when you open Amazon.com, how long do you think it's, it opens up a page with like those 10 products to show you on the front page, right? Something within less than a second for sure. And in fact, when they open that page, there are different departments in Amazon whose time budget is like, okay, you have to show what are the delivery options in 50 milliseconds. Hey, you have to show the assortments in the 100 milliseconds. You have to show XYZ in some other milliseconds. So each department has a budget of, to meet. Okay, and we have, this application shows that you can actually do that with choice modeling at scale. Okay. Any questions there before I switch back to choice models themselves? Yeah.
Just wondering, like when you were saying the ML model, the choice model we are making, it's kind of equivalent like in the machine learning area, like for this machine learning, like nearest neighbors. Like I just wondered for this transformation part, like the back here, is there any like theory, like some like back up for this kind of theory?
No, so this MNL enables that mapping to a nearest neighbor problem. Other richer choice models that I'll show you next, like a deep learning based model, that doesn't map to nearest neighbor search. Okay, and this mapping, so in the field of optimization, people always do these what are called reformulations. So you write in an original problem, maybe it's an LP with some set of constraints. You may be able to reformulate by changing, defining, stating the same problem in using different set of variables, which will have maybe lesser number of constraints or more constraints. So people keep reformulating, and so we just reformulate the original assortment optimization problem if you use the MNL choice model into essentially a nearest neighbor problem. Nearest neighbor problem is also an optimization problem. It's like minimize the find the vector which is closest to the reference vector among all the vectors. It's also an optimization problem. Okay. Yeah.
Talking specifically to the retail problem that you mentioned with regards to the Walmart.
Yeah.
When you said about 500 cookies, if you talk about the choicing itself, it could be millions of combinations itself.
Yes.
When you define in terms of which choices to give, let's say, to a consumer.
Yes.
And generally, like the consumer pattern itself is completely different. It's very individualistic.
Yes. Yes.
So how do they determine that? Because that's the next step to the heuristic model and all that, right?
Yes. So I think it's a great comment, and let me pick up two elements that I think are interesting. Firstly, there is so MNL model here. I said there's one number per product. Okay. There's one number per product per customer type also. You could make it like you can segment your customers, whole universe of customers into these types of segments. And for students, maybe these are the parameters, and these parameters lead to this type of assortment of cookies to show to them, for example, compared to working professionals or some other group. So you could do per segment, you could have a model like this, but still not expressive. It's still not expressive. And you are right that even for the Walmart situation, if you want to go from 21,000 to 500, there's so many combinations. Okay, you can't literally even enumerate them. But if you restrict yourself to if you restrict yourself reasonable model, then you can actually still deal with that huge combinatorial explosion. Okay, but let me actually come back to that. So I took those two elements. I know you had maybe something else also, but let me come back to this problem of explosion, right? So the whole purpose of modeling, I don't know, like there are different types of models, but the whole purpose of one of the key purposes of modeling is to actually do that reduction in like complexity. Okay. So we'll see one of those applications right now. So let me switch back to the engagement problem. Let's talk about Twitter, because Twitter has to obviously show you tweets within milliseconds, right? When the moment you open your app or you keep scrolling, it has to show what's the next thing which will keep you engaged. Okay, it doesn't want they don't want you to leave the app and not just Twitter, TikTok, or anything else, right? So clearly they need to optimize based on the user's interest and other things, okay, trending things and user's interest. So this problem is like, it cannot be just a simple MNL problem that you solve once and you're done. It's a more complex problem. Here what I'm trying to say is that, this showing the few tweets, given tons of tweets for this user, you can actually forget about choice. You can just say, okay, I'm going to just solve it using what is called recommendation algorithms. Okay, I don't know if you've seen recommendation approaches, which basically try to recommend, oh, here's the things that you should see, given your profile, given everything else you've done on the platform. Okay, so but we still, we are operations people. We think that there's a choice effect between tweets. Okay, so maybe if it's a tweet about the same event, let's say Australian Open in tennis, if there are like 4 tweets on the same thing, then me interacting with one of those tweets gets influenced by, in fact, it gets decreased because it's the same tweets elsewhere. Okay, so, and especially let's say you're a musician and if you get a tweet related to sports, you're probably not even going to interact, right? So there is we think that there is a choice effect. There is a effect of other tweets on what you do with one of these tweets. Okay, that's the angle that we want to take, and that's something that recommendation systems don't do. Okay, I mean, maybe they'll do it implicitly because they learn from large amount of data and they'll surface the things that you might interact with, but it's not explicitly captured. Okay, but we want to do that explicit capturing. But instead of working with tweets, what we're going to do is, there are too many tweets. Okay, and every tweet is unique, right? There are billions and maybe even trillions of tweets now. Every tweet is unique. We can't really model each tweet as like a product. Okay, it itself cannot be a product or an item to optimize for. So instead of tweets, we have to map it back to something coarser, like tweet topics, or some coarser level representation. Like maybe this tweet is about music. Okay, this tweet is about a certain type of sports, and so on. So you make it coarser, and then you have a little bit more manageable set of products or items to optimize over. Okay. So what is the actual ML part? What is the analytics part here? Is we saw the MLL model, the simple, it looked like linear regression. You just had one number per item. Instead of that, here we will actually have what is called, I guess, a neural network. I don't know. Some of you might have seen a neural network before, and some of you might not have. It's not super critical for us. This bunch of boxes with some arrows connected in them are just trying to represent this capital P that we saw 3 slides ago. So the probability of choosing an item given a set, right? So what is that given a set is this is a set that we give as an input. So the set part is from here. Engagement history and engagement frequency are parts of the user, in the sense that user has some engagement history. The user has some frequency with which they engage with different tweet topics. And then we want to say, okay, if that is the case, if these are the user characteristics, this is the first 2 parts, and these arrows just mean some computations for now. Okay. If I show these 5 topics, okay, maybe sports 1, sports 2, music 1, music 2, and so on, then what is the probability that they will actually like or retweet or reply to those tweets? Okay. So this graph is just, the graph is drawn to kind of appease the neural network folks who like to draw boxes. Boxes just represent some collection of numbers as a vector or a matrix or something like that. And these arrows just represent there's some transformation going on. Okay, so it's just given a vector, I got some other vector. From that vector, I got some other vector. And finally, I got what I need is just the engagement probability, the probability that the user clicks or whatever, in our case, engages with the tweet given the engagement history and frequency and what I want to show them. Okay, that's obviously part of the input. Let me skip that. So that is a choice model that we built to capture the choice behavior for the tweet setting. So we had some data from what is called recommendation systems challenge. As I said, there's a bunch of people in recommendation systems area who build these types of models, but we wanted to capture choice. So we had about 100,000 users and 2.7 million tweets, which is like a drop in the bucket. Actually, each day you may have like billions of tweets happening, or at least at the scale of a billion. But it's just to show some like the value of building like a nuanced model, like a choice model here. So here, actually, let's not focus on the numbers. All I want to show is that there's a bunch of models that can all surface things that you think the firm can think that user is going to engage with. Okay, so many of them are actually just going to be recommendation models. Okay, there are some different acronyms. Let's not worry about them. And here's a choice model. Okay, the choice model happens to be not MNL anymore because we want to specialize the model to the user's interests and their previous interaction with the platform, right? So that's the model here, and you can see it has high means better among, there are some metrics in machine learning beyond classification, right? Classification is just whether you're correct or wrong, but here the metrics are something else because you want to surface the most interesting things and not surface the things that are not interesting. It's a different metric that you can measure using, to measure this. And we have, we just show that we can do slightly better, but also in terms of what we care, which is engagement optimization. Given that choice model, we can also actually optimize for what tweets to show. Okay, not just build a prediction model of whether this person is going to engage with the tweet or not. And we can do an explicit optimization. We can also show that we actually have an uplift in engagement as well. Okay, this is all offline data. We did not do an A/B test. Obviously, we didn't work with Twitter itself, but this gives you a flavor of how to bring in choice modeling, historically a revenue management topic, to other areas that are relevant now with the web. Okay. Any questions here? Yeah.
Where was the revenue part considered?
So in engagement maximization, there's no revenue.
But
yeah.
The Walmart example, I think.
Yeah, there was prices. So there was no cost, but there were prices, right? So this P is you can think of as the revenue from if the customer actually purchases item I or chooses item I, then this is the dollar amount that I get. Obviously, there's a cost part of it. That's why this is just a revenue maximization problem.
Okay, yeah. So it could be weighted either if the revenue is very high, probability is low.
Yeah,
that also.
You may still be interested in showing that. Yes, you'd still care about maximizing money, right? I mean, you want to be profitable. Yes. Yeah. Okay, let's actually switch. We may not be able to cover all applications, but let's switch to something different. Okay, it's not going to be operations heavy, but it's going to be interesting for the part that I mentioned at the beginning, which is there's always going to be a lot of analytic tools available, and you as a domain expert have to figure out which tool to use. Sometimes the tools are ready-made. Okay, it's just literally download and insert your data, and you may get something interesting for your business. Okay. But many times there's actually a gap, and somebody has to bridge that gap. Either the person who built the tool, okay, the person who builds the deep learning model, the person who builds something, or it has to be the domain expert. Okay, so I want to show you an application where we can, somebody has built a tool which is going to be some model, and we'll do some extra steps so that we can actually use this for our application. Okay, and our application is going to be in transportation manufacturing. In particular, what is the tool I'm talking about? The tool, what the tool does is interesting. It actually works on images, not tabular data. Okay, and the tool actually puts boxes around interesting objects. Okay, that's what the analytics tool, in this case machine learning tool, is supposed to do. Okay, this problem is called object detection. It has various applications, right? So you can do aerial imagery where you can detect, let's say if there's a disaster region and you want to find people among a lot of debris, right? So you can do that. Here is just a transportation application where the tool is trying to figure out, okay, where's a vehicle, where's a human, where's other objects of interest. Okay, so this is what the tool does, but the tool doesn't do a good job, even in this situation, because there's varying sizes of objects to detect. Okay, so I will show you a graphic later where we'll see that the tool doesn't do a good job off the shelf, and we have to do some improvement. Okay, that's where you can bring in your some sort of a creativity hat and figure out how to create how to bridge that gap between an analytics tool and your domain, your problem. So the problem that we have is actually that when the tool detects puts these boxes around objects of interest, the tool does a bad job when the objects are really small. Okay, that's the core problem. If the tool was able to do a good job when the objects are really small with respect to the image, then there's nothing to solve. It's just that as of today, the tool is really good at finding bigger objects, but it's really bad at finding small objects. Okay, and we want to do some extra tricks so that we can make the tool do a good job even on the small objects. Okay, that's literally the goal here. And one of the ideas to do that is called tiling. Okay, and we'll see what tiling is. It's just a nice post hoc trick. You're not doing anything. You're not building a new model to detect objects, but you're doing something extra so that you can actually use it in your application. Okay, hopefully you can see, you can do these types of tricks in other applications that you are concerned with in operations and supply chain and so on. Okay, let's see what the trick is. The trick is actually very straightforward. If you have a big image and you want to detect small things, then why don't you just take parts of the image and pass it to the tool? Okay, you just take a small part of the image, pass it to the tool, pass another part of the image, pass it to the tool, because in the small parts of the image, the object which is small with respect to the big image is actually reasonably sized with respect to the smaller part of the image. Okay, that's the idea of tiling. Okay, and once you find, in smaller boxes, whether the object is, whether object of interest is there or not, you figure out, okay, how to merge all these predictions so that you actually have, objects of interest in the full image. Okay, so you just have to, it's like divide and conquer. You pick each part, find the objects of interest, and then somehow merge them together. Okay, that's the key idea here. It's called tiling. And basically, why do you want to do that? Is because we want to achieve efficient, disparate sized object detection, which is we want to detect big things, but we also want to detect small things. And this comes up in transportation that we briefly saw. It also comes up in manufacturing that I'm going to show you in a minute. And what we want to do that, and we want to do that when we are actually model agnostic. Okay, in the sense that we don't want to actually build and go and hire people to actually build new models from scratch. Okay, that's probably hard. And maybe if you're Facebook or OpenAI or something, you can build big models, but maybe a typical business cannot. So we want to be model agnostic and figure out this gap between analytics and your domain, the operations, and see if we can bridge that gap. Okay, and that's this example here. And I already told you the idea, which was pick parts of the image, pick small parts of the image, do the detection, and then stitch solutions together. Okay, that's pretty much the idea. So I'll skip a couple of slides which elaborate on that idea, but that's the core idea. Let's actually look at the results, okay? Because that's where I think some commentary, and I can give some commentary. So this is the original image. It's the same image as what we saw a few slides ago. So this, you can see that this is not a typical, like if you do machine learning, maybe instead of 101, like a 201, even there, I don't think you'll get to deal with so many objects in one image. Okay, maybe there's one person, maybe there's a cat, maybe there's like 5 people, and that's it. Okay, this image is actually a typical image in this application, right? Especially like Southeast Asia or South Asia, you're going to have tons of cars and tons of people in one field of view. Okay, so this is the original image, and with much of machine learning or analytics, you actually need someone to go and say, okay, in this image, these are all the objects of interest. Somebody has to annotate the data. Okay, many times you will get you may get a ready-made data set where these are the inputs, this is the desired output. Somebody might give you, but in many situations, especially image object detection situations, you have to actually hire a bunch of people and make them, okay, this is an object of interest, this is an object of interest, and so on. Okay, it's a multi-billion-dollar industry, and here's the situation, right? So there's a bunch of people over here that even the annotator missed, right? I don't know if you can see the people, but there's actually people at the top which the annotator missed, and there's actually a bunch of vehicles here that the annotator missed. This thing in the red, the bunch of vehicles here, the bunch of bikes and bicycles and so on, the annotator missed. Yeah, go ahead.
I think pretty much all of us in the room have been annotators at some point because of reCAPTCHA.
Okay.
reCAPTCHA basically.
Oh, reCAPTCHA, yeah. Google reCAPTCHA, or yeah.
But that's basically training an AI model.
Yes. Yeah, you probably are not doing object detection, but you are doing classification though. Yeah. So here, all I'm saying is that in applications, sometimes the data is not even going to be correct, right? So you will have to do something here. So with our without the tiling idea, so this is just somebody built an analytics model. I just want to use it in my application. You're going to have a lot of misses, right? So for example, where you see the boxes, the model said here's something of interest. Okay, Where you don't see the boxes, there may still be something of interest. As you can see, there's a person on a vehicle here that the model missed. Okay, there's a bunch of people walking here, a bunch of people sitting over there. The model missed. Clearly, the model missed these bunch of bikes also, right? So that's the gap. That's the gap between somebody giving you an analytics model and you're just using it, and it not performing to what you want, and then you're figuring out, okay, maybe I can do something interesting, something clever, and maybe fill that gap. And that's the next. This is the solution with the tiling idea. With the tiling idea, you should pick parts of the image and pass it through the same prediction model, get the annotations, get the predictions, move to a different region, get the predictions, move to a different region, get the predictions, stitch them together. And you can see that in this case, we actually got even the people that were not annotated by maybe not these people here, but some of the people here, these vehicles here, which were not even annotated in the original data. Okay, so what I'm trying to say is that there's always going to be gaps that you can fill and therefore actually do well in applications. Okay, and here's one last one for since it's in manufacturing. Here's one that we built, which is kind of not showing too many objects in the same image, but these small objects. Okay, so obviously here these are not small objects, but you'll see at some point that there's going to be small defects in this clothing product, in this textile product, where you want the computer vision model to work, for which it's not easy to, if you train a model, which you saw some small boxes here, right? So it's not easy to retrain everything from scratch and still detect small things. Okay, we are actually able to detect smaller. I mean, obviously these are bigger, but there are some instances that you saw where there were small bounding boxes. Okay, to be able to do that, you need those extra tricks. Okay, and that tricks is, I mean, you as a domain expert will know actually what is that you want. The tool builders, okay, the machine learning folks may not be as good as you in figuring out these simple ideas that can actually make the existing tool work for you. Okay. Any questions here? Comments? Okay, so yeah, so I wanted to show an application where it was not so much heavy on operations, but trying to focus on this gap between analytics as a tool and you as a domain expert trying to use them for your businesses. Okay, the last idea is also very simple, so let me briefly mention it. Yeah.
Sorry, I just have a question that you just mentioned. Like, if I'm a domain expert,
yeah,
how should I tune this kind of
So we're not tuning anything, right? That's what we're being model agnostic in the previous example. We don't know how the model was trained. We don't even know the complexities that go into doing whatever is needed to get that detection model. But because in our application we knew that there were small things to detect as well as big things, how do we detect them simultaneously? If I just apply the tool on the full image only once, then I might miss the small things. So very simple naive idea is to tile, which is just focus on region by region. Because in that, if you only focus on a small region, the small objects will look bigger. Okay. Obviously, that's not a bulletproof solution, because once you zoom in, maybe the small objects looks very bad, and so you can't really identify that that's the object of interest. Okay. There is obviously some limits to the trick that I showed, but you're not touching anything. For you, the analytics tool is still a black box in my application. Obviously, if you learn. So you as a domain expert are actually in a great position to learn machine learning. Okay, that is actually going to be more helpful than a machine learning person who's only trained in statistics being able to help in a domain like manufacturing or transportation. Okay, you need to recognize that strength, and you should play to that strength. Okay. Anything else? Okay, let me briefly mention the last application, mostly because I don't know if you have not yet tried out any LLM, you have to try it out. Okay. It's like seeing is believing. So you have the access now. I mean, maybe you have to pay a little bit of money, but you should try out ChatGPT or any of these Bard and other things. What we're going to show here is again very similar to the previous example, where there is a tool. It does amazing things for maybe individual customers and many people. But I want something to be done. Can I just use the tool with some extra tricks and achieve what I want? Okay, so that gap between analytics tool and you as a domain expert. Okay, let's fill that gap. And here's the second example. So what do we want to do? Me as a business owner or a leader or management, I want to understand what's going on from one source of data, which is news. Okay, news and news articles and news headlines. I want to make sense of this unstructured data. Unstructured only because it's not tabular, right? It's not a bunch of numbers that I can visualize and things like that, right? So it's a bunch of textual data. I want to make sense out of it because maybe I'm competing. So maybe I'm one of the firms who is in the news. Okay, maybe I'm one of the firms in the news, and I'm being talked about with other firms. Maybe other firms are being talked about in my market. Okay, so all that information is there in this unstructured data, and I want to make sense of it so that I can understand who are my competitors, who are my partners. Is there some new partnership that I can form, and questions of similar nature, right? But to kind of answer those questions, I need to somehow go from this unstructured data to something that is a little bit more manageable. And for us, okay, one of the manageable things is a graph. Okay, a graph with maybe nodes representing maybe companies, maybe edges representing their relationships, something like that. Okay, you could have some other ways to compress, go from that unstructured data to a structured data set. But here, we want to get to a graph. Okay, how do we do that? How do we do that with zero training? Okay, that's the, just like the previous application, we don't want to do training. For us, the analytics tool is a black box, and we want to kind of exploit it for our purpose. Right? So let's say we have a data set. Okay, this is like, in my case, I had a data set from a vendor, not news vendor, but he is vending news here. So here's the way to use black boxes. Okay, these things that you see with some names, I'm gonna mention them. The yellow box, the white box, and the blue and yellow there, they're all black boxes. They are all analytic tools that you can use to go from, what is it? So you can go from this news data on the left, lower left side, to data that looks like this. Okay, which is a little bit more structured. It's a data with potentially either the nodes are the companies themselves, or maybe products and relationships between them, and also the strength of the relationships. Maybe there's a negative relationship between two products or two companies, and maybe there's a positive relationship between two products or two companies. Okay? That's what we want to get to. Go from a bunch of documents, basically news articles, to some graph like this. Okay, and we want to use all these boxes. Okay, and actually, let me simplify that by saying we can actually go from data and use those boxes. Actually, it turns out GPT-3 or GPT-4, for example, these are examples of I guess instruction-tuned language models, large language models. You can actually get to the graph directly. Okay, either using any of these LLMs that we're talking about, or you can use separate capabilities, which are also like LLMs, but they're a little less popular, to also go from data to this type of graph. Okay, so how do you do that? Is given the time limit, I'm not going to get into the detail of how to go from a news article to a relationship, but let's briefly look at it through examples. Okay, a couple of examples. So let's say this is let me just even focus on just the headline. Okay, let's say the headline says Facebook paid a GOP firm to malign TikTok. Okay, GOP firm is some political entity, I guess related political entity. So let's say this is the headline. Okay? It turns out those boxes that I showed, okay, these are just plug and play. I just show the acronyms in the previous slide. I can discuss them more later, but if you just use this news headlines as an input to those boxes, they actually tell you, okay, in that headline or in that news article, there's actually Facebook, there's actually GOP firm, and there's also TikTok. Okay, they can recognize the entities without you pre-specifying, okay, I only want to look at these, these are the companies that I care about. You don't have to even do that. Okay, completely data-driven way, they'll tell you what are the companies that are involved in that news article. Okay, and not just that, the the same black box can also tell you for every pair of entities in that thing that you extracted, what is the strength of the relationship. Okay, it's just it's you don't train anything. It's a pre-trained essentially language model equivalent, and it can tell you, oh, if it's Facebook and TikTok, it's a negative relationship with some score. Okay, some normalized number between 0 to 1. Okay, and this is with numeric scores. If you just ask GPT or GPT-4, for example, with the same headline, okay, Facebook paid some firm to malign TikTok, GPT-4 can also tell you, okay, what are the entities in that statement, and what is the relationship between each pair, Facebook and GOP firm, Facebook and TikTok, GOP firm and TikTok. For example, Facebook and TikTok, the relationship appears to be negative as Facebook paid something. I mean, it's actually giving an explanation. Okay, maybe it's not very elaborate, very transparent, but it indicates a harmful intent towards TikTok, for example. So you can actually just literally use the tool to learn not just entities in each news article, but also like relationship between them. Okay, that's the simple idea here. I want to not show the very messy graph. This is just Apple centric with just Apple and everything else. It looks very messy, but let's focus on one example and close this application. Here's what Apple did, right? So here's what I'm showing is Apple, Meta, Microsoft, Google, and Amazon. This is before April 25, 2021. Okay, 2 years ago, Apple said we're gonna protect our customers and we're not gonna let companies track more than what they are allowed to. Okay, basically a privacy change. And you can see before the privacy change, the strength of relationship between Apple and Facebook. Facebook heavily relies on advertising and understanding people. Same thing with maybe Google as well. So many of these companies, right? So Apple did the privacy change, and next you can see just based on the headlines, the strength of the relationship between Facebook and Apple went down by whatever the normalized units were, from 0.71 to 0.15. And this is something that you can very easily get by just having those black boxes, run through news articles every day, every week, or every month. Okay, you're not doing anything beyond that. Somebody else has built that nice analytic tool, in this case a large language model, and you can learn the strength of the relationship. For example, I think Apple and I guess Google, the strength of the relationship didn't change too much because they're actually two different ecosystems. The Android ecosystem and the iPhone ecosystem, they don't get, I guess they do get affected. Google gets probably affected by advertising, issues, but it's not too much. Okay, so just to summarize this section, here, again, a very straightforward idea. We had unstructured data, and we have these nice tools in the analytics field. We actually could use it to extract entities. Entities are these firms and maybe even products, and infer relationships, and not just infer relationships, but also strength of the relationship, whether it's positive or negative, and not just positive, negative binary, but also some numbers that you can calibrate. Okay, and you can use them obviously to inform decision making at a strategic level. It's not very operational. It's not a day-to-day operational tool, but gives you a sense of what you can do. Okay, so let me wrap up. So we saw 4 applications. Mostly, obviously, I did not get into any depth with any of them, but 4 applications that show the potential of analytics tools, right? In applications which may not be exactly operations and supply chain management, but also related fields. Okay, so I'm just talking about more from an operational perspective. We as domain experts can actually use these analytics tools, and the applications were crowd shipping, choice modeling, computer vision for automation, as well as business uses of language models. Okay, so we just saw those 4. So I just want to conclude by saying that there's a lot of possibilities that are not yet explored. Okay, I just showed you some tricks that I kind of, I as in me and my colleagues, we probably thought, okay, maybe it's a good idea. We tried it, and maybe we showed that it works. Okay, but the space of possibilities of like coming up with these interesting ideas that can bridge and help you use these tools beyond some ready-made tool is where I think there's a lot of potential, and the first mover advantage is going to be there if you can recognize that and actually think in that direction. Okay, so analytics, as you know, can be a force multiplier, and especially it can be a more force multiplier now with the era of big data and large data and so on. And hopefully it can help you be motivated in learning about the sibling field while you be the domain expert in your field. Okay, you don't have to. You actually have a better advantage than people who know analytics but don't know much about operations or management. Okay, that. Let me stop. Any questions about the last application or anything? Please go ahead. No questions? A lot to think about. I'm here, so if you have anything to discuss, you can also reach out to me separately or online on my web, through Twitter and stuff. Thank you.